Hello and welcome back for class of structural analysis. So we will continue the chapter number 1. Actually, it should be here. Chapter number 1. This will be the second video on this chapter number 1. And today we are going to start to see this part from 2 to 6. Okay. Next time, the next video, we will do some 2 or 3 exercises before ending the first chapter, number 1. So let's go with the definition. Introduction we did last time in the previous video. Definition. So the resistance of material or material resistance, study the effect of forces, the effect that forces produce on a structure. Okay, and it allow to determine the condition which the element of our structure, means slab, column, or beams, how this element of the structure must meet so that they can stand the forces coming on them. So this is what is this resistance of material resistance. This is the meaning. Okay. Study of the effect of the forces that are acting on our structure or element of our structures, beams, columns, or slab, or any others, and investigate what are the requirements for this element of the structure so that they can stand the forces, they can support these forces coming on them. Okay. When I say solicitation here, solicitation is just the forces coming on the element. Okay. So in engineering, we prefer to work with constants. Constants here means stress, actually. Okay. The translation is not good. We prefer to work with stress instead of forces. We don't like to work with forces because constant is ratio of force to the section. Okay. Force divided by section, that give us stress. So normal stress, okay, we should replace a constant here by stress. So normal stress is when you take normal force and divide by any section. Okay. We prefer to work with stress than force. So that's why the definition of stress is very, very important here. You should understand. The sigma here is normal stress. The normal stress here is an illustration. You see this element, it can be a column or anything else. This force is coming on this element. And if we check inside, we do a section, we can see that if we divide this force, the normal force coming on this section, we can get sigma, the normal stress, like this. Okay, this is in case of compression. Okay, means the element is compressed. In case of traction, it's same. Just force divided by the section, force divided by the surface, this area on which this force is acting, and we can get the stress, corresponding stress. Okay, let's suppose this case for example, of the beam being loaded, okay, uniform loading, for example, this beam, okay, the force here, the surface on which these forces are acting is this surface, on the surface of the slab, okay, not like this. No, it's not always in this case, but the surface, the section perpendicular to, when the section is perpendicular to the force, we are going to talk of normal stress. Okay, we can see another illustration here. This is like, can be the constants, the columns, for example, and the force is coming here, and we can see if this is slab, the bottom of this slab will be subjected to tension. Okay, however, the upper part will be subjected to compression. But anyway, the normal constant will be the area where the force is acting will be used and in this formula to obtain the stress. Okay, so the principle of material resistance, okay, this is material resistance, are based on the law and theorem of general mechanics. Okay, actually here mechanics here means physics, and primarily it's based on the law of statics. Statics means stability of bodies. Okay, however, it not always normal stress, normal force. Normal force divided by section or area is when the force, normal stress is when the force is normal force. However, we can have also this kind of force, sharing forces. When the force is normal, let's consider this section up or bottom. This force is normal to these sections, right? Here also, the force is normal to the section. However, we can see here, same section, these two forces are not normal to the section. Okay, they're not perpendicular to the section. They are a parallel to the section. In that case, we will have sharing stress instead of normal stress. So be aware that it is not always normal stress. Here is another illustration. In case of three-dimensional view, if we take this cube, okay, this box, for example, on each face, let's take x-axis, y-axis, and z-axis. We have here two type of forces: normal force and sharing force. See this face, for example, if we take this is sigma, means normal force. The force is normal stress because the force is perpendicular, normal to the section, to the face. However, this one, tau, this force is, let's say, tangent or parallel, tangent to the section. So we are going to talk about sharing force, sharing stress. Okay, same here in two-dimensional view. These forces, this one, this one, this one, and this one, these four are sharing forces on the top. This one is for the top face. This and this one are for the side faces, and this one is for the bottom face. Okay, these one are the normal ones. So normal forces will cause normal stress. All this just to tell you, we may have normal stress or sharing stress. Okay, please remember that. It's very important. So this is about definition. Let's go now on the third part of this chapter, deformation of material. Okay, what can we say about this deformation? How material can deform? Okay, so every material you take, no matter what kind of material, wood or concrete or steel, every material under action of external force, the material will tend to deform. So every material deforms under the action of external force. And after releasing the force, after the force stop acting, the material is standing to return to its original form, original position. Okay? No matter the material you have, if you apply force on it, external force, the material will deform. And if you remove the force, you stop applying the force, maybe the material will is standing to regain the original force, original form. Sorry. If you take the case of this beam, for example, applying these uniform forces, you will see that the beam will be bending. Okay. Here is another illustration. You see here how the beam is bending. So deformed. Bending means deformation here. Illustrates with deformation. So another example here, let's consider this is, for example, a bridge and bridge piers, or let's say this is slab or another beam. So when cars moving on let's say a row of cars moving on a bridge, for example, the bridge may deform like this. Okay. The deformation may be not visible, but there is still deformation. Sometimes you can see the deformation actually. If the load is very high over the limit of the bridge, you will see the slab, the bridge deforming like this. Okay. So we can try to find relationship between stress and deformation like this. See sigma here in the y-axis, and here is deformation, which means each force, each stress will correspond to a deformation. Some people don't understand how this curve can be obtained. Why is it like this? And why it is not just one line? Okay, why the curve is going this way and coming back this way? If you check the arrow, this arrow means this way, and this arrow is this way down. Okay, so this means simply that when you apply, you increase the force here, displacement corresponding. You apply force and displacement here, force, displacement. When you reach this point now, instead of continuing applying, the force is decreasing. The force is decreasing, the amount of force, or you stop applying the force. And once you stop, so the material will try to recover its original form, its original shape. Okay, so that's why it will come back this way. However, the material will not recover all the deformation you caused, the force applied cause. So the recovery will not be the same way. It will not be same speed of recovering. Sometimes if you take plastic, okay, and you pull it until a certain point where the plastic deform, with large deformation, if you release your force, maybe the plastic will try to regain its original form, but it will not be at the same speed as when you were pulling it or deforming it. So that's why we have this curve. Instead, it will not go back in this way. The material will go back in this way, but it will be the same. You will have another relationship: stress, deformation, stress and deformation, stress and deformation. Okay, so it means in this case here, from here to here, the corresponding deformation caused is here, this amount, the total amount here. However, when you stop applying load here, the material came back here. If you see this point, the load applied is 0. It means the stress is 0. However, the deformation, you still have this deformation, not recovered, completely recovered. So that's the problem. When you apply too high stress to a material, it may not recover the original form. It will try, for example, here, you see, it will try to recover everything, but reach and it is stuck here. So it did recover all this. However, this part is not recovered because the point didn't reach here. And you will notice that if, for example, you start doing here, if you stop here before going too far, maybe the material will come back here. It's just a matter of where you stop applying load. If you go too far, it will not come back this way. It will come back in another way. So if you apply again here, it will go maybe this way and come back again, and so on. Okay, it will not follow this way again. It will do like this. So this delta L, delta, we can call it relative deformation. Okay, means, please understand what is delta L. Delta L is the amount of length that increases or decreases. Supposing you have a material, the size, the length is 10 centimeter, and you pull it to 10.5 centimeter. It means you have added by pulling 0.5 centimeter. So your delta L will be 0.5 centimeter. It can be, you can so calculate it by saying it is the final length minus initial length. So 10.5 minus 10. And you divide by the original length, initial length, which is 10 centimeter. It is same when you also do compression and you reduce the size of the material. Let's say, for example, you do compression and you reach 9.75. It means you have reduced it of 0.25. 0.25 will be your delta L. So 0.25 divided by 10, the original length, will be this. Okay, relative deformation normally. I hope you understand what I mean. So the deformation of any, when I say body here, it means material. Okay, we can separate it in two parts. I think I have already explained that, the deformation, and it is here. The first part is elastic deformation. That one is the deformation that you can recover, the material can recover. So that deformation stops when the forces causing it stop. Okay. And another one is permanent deformation. That one remained. If you go far, the material will not recover totally. And this is here. Permanent. This is in French, by the way. So deformation, you can see So elastic and permanent. So it means when you apply the load up to here and you reduce the load up to the material will try to recover, it it recovered this part. So we will call this elastic deformation, elastic. However, this part is already finished. We cannot recover this part already anymore. So it will be permanent deformation. And if you apply again, you will start from here, not from here anymore. So it means this, you have lost this part. Okay? Deformation. Okay. So what is now about the construction material? Because our objective is the construction, the material we are using in construction: concrete, steel, wood. Okay, these are the main material being used in every daily construction. So for this material, the permanent deformation can be neglected as long as the stress does not exceed a certain value, certain limit. The limit we call here elastic limit. What is elastic limit? Elastic limit is, for example, this. You can see here two color, green one and red zone, green zone and red zone. Okay, this is in French. Okay, but I think you can understand easily. So if you apply still relationship, stress deformation, okay, we see sigma, right? Okay, stress and deformation. So if you are in this zone, this zone is called elastic zone. As you can see, it's like a portion of its straight sigma. This sigma, this portion is linear, as you can see. So if you apply the stress and you limited yourself in this zone, see, stress deformation, stress deformation, stress corresponding deformation. Up to here, RE, stress deformation. If you are in this zone, this limit, you can recover the deformation. The deformation will be elastic. However, if you go above this point, the deformation will be plastic. This is plastic zone. You will not recover all the deformation caused by the stress. So here, the elastic limit is this limit, okay? This zone, elastic limit. So as long as you stay in this, you can neglect the permanent deformation. That's why for any construction project, you need to stay in this zone for all material. So we need to know our material because this curve is different for each material. The value here, the limit value here, the maximum constraint and the maximum deformation supported for each material for this limit zone, elastic zone, is different for concrete, for wood, for steel. You have to know this curve or at least the maximum for each material. Okay? I hope this is simple. Let's go now to the Hooke's law. This is very simple. Deformation of any material. When I say body here, it means material. Okay? is proportional to the force which causes this deformation. It about the same thing we just did now, the deformation we did in the previous section, section number 3 of this chapter. So this section number 4 will be based on the previous one. The force, the stress, and the deformation are proportional when you are in the limit zone. The limit zone we have just defined, okay? This linear part of the stress deformation curve, the stress deformation relationship, the linear part of this stress deformation relationship has, as you can see, domain, linear domain is here. This part has proportionality between the stress and strain deformation. The deformation here, relative deformation, is just strain, okay? So far, we didn't talk about the strain, but this is just strain. I think in English, this is called strain, not deformation, actually. But in French, this is relative deformation. Strain here. So when I say deformation here, consider it as strain, okay? So I'm French native, so please understand sometime. Okay, so if we take this, see, the same figure we used before, this zone is the zone where we have proportionality between the stress and strain, stress and deformation. Okay, this limit zone. So as long as we are in this zone, we can define the relationship, and the coefficient of proportionality is here, E. Okay, so in the linear domain, this domain, the stress is given by this expression, sigma equal E multiplied by epsilon here, deformation in French, strain in English. So here the E is representing the slope of this linear portion, OP. The slope. Slope means delta Y divided by delta X. You know that, right? So slope, if you say, for example, this distance divided by this distance, okay? We call this longitudinal modulus of elasticity, or just modulus of elasticity. But this one is longitudinal because the force is an axial force or normal force, if you want. When the force is axial force, we talk about longitudinal. In French, my pronunciation here is like in French, longitudinal for modulus of elasticity. I think you understand. So the E here is also what we call Young's modulus. The Young's modulus is just this one. So Young's modulus is nothing but the coefficient of proportionality between stress and strain in the linear zone. Please remember, in this zone, not here. If you enter this zone, we are not working in this zone. This green zone, not in the red one. Okay, Young's modulus. Okay. Do you remember this? Share forces, share strength, share stress. Okay, sharing stress when the stress is tangent, when the force is tangent to the section, to the area, then we talk of shear stress, sharing stress. Okay. So in case of sharing stress, we also observe stress strain relationship, proportionality. In case of transverse force, means shear force. Okay. Here, if you take this two-dimensional case, it's same here. See, T here. However, here is tau, here is T. Just a notation problem. It's same. So here we have this stress, which is tangent to the face, another stress, okay? And it's like when you take your hand and you put on the table and try to push like this, sharing force, okay? You push. When you push hard, you may deform your table if you are strong enough, okay? So when you do that, this, supposing this cube, by pushing this force, for example, you can deform the cube. It will deform like this. In soil mechanics also, we have something like this. So you will have an angle here, or this delta, vertical one or horizontal. Okay. So T here is sharing stress, shear stress. Okay. The shearing stress can be obtained with this formula. Okay. G multiplied delta V dV dx, or again G multiplied by this gamma. Gamma is this angle here. The definition of each term, this gamma is distortion. Okay, this angle of distortion, this distortion. G here is transversal modulus of elasticity. So, do you remember the other one? E, we talk about longitudinal modulus of elasticity in the previous slide. Okay, then T here is what I said before, shear stress. Okay, sometimes you will see here that as tau instead of T. Okay, it depends. So transversal modulus of elasticity, but sometimes people just say modulus of elasticity. That's all. And the E is Young modulus. Okay. Let's now talk about Poisson's ratio. That one is very easy. I think everyone understands that easily. So this Poisson's ratio, when you take a material, any material subjected to axial force will undergo a variation in length. Okay, if you take a duster, for example, and you pull it or you compress it, it will change in the direction of the force of the load, but it will also change in the direction perpendicular to the load. Okay, if you take your duster or any object, if you compress it, the shape will change in this direction, but this direction also there will be a change. Okay, if you pull, maybe pull here, change, but this way will be reducing. Something like this. If we compress, this original shape is this one. This is the original shape, for example. Okay. And if you use these forces applied to compress this object, we will have this shape, the dash line. Okay. See, the original shape, E here is this dimension, transversal dimension of the larger, and L is the length of the object. original length. So what we are calling here the ratio of the Poisson ratio is just ratio of lateral strain to that of axial direction. Okay, and this coefficient, maybe this symbol means nu or what. So lateral deformation, this one is not translated because normally it should be from French. Okay, but you can read, try to read in French. Deformation here means lateral. So lateral deformation, that is to say lateral strain, okay, divided by axial strain, axial deformation. Okay, so delta E, it in French, but you understand, I think. Delta E is the variation of this in this length. Okay, what I explained this before. You say you take the original, the final length minus the original length, and you will get this delta. Okay, the final means this from here to here minus this E. It means in that case you will get delta E divided by E, and delta L means this final length, and you see this, the original length is this. In that case it will be negative, but anyway, the delta L means the variation of the length divided by the original length, and you will have this. So this divided by this, you will have this this Poisson ratio. So each material also has its own Poisson ratio. Steel, concrete, wood. Okay. Let's go to the final section of this chapter, the final section of this video. Okay. Before last of this chapter, next video will be just exercises. Okay. So this study, structural study, any structure or any structural study begin with deformation of the determination of this support reaction. Okay, what are the reactions of the support? This being said, it is also necessary to determine the stress, not constraints. Okay, the stress inside the structure. We have to determine the stress inside the structure. Okay, it's like something like this. We have this. Let's suppose that this is beam. Okay, even if it is not a beautiful one, just a beam. And on this beam, you can see forces acting on the beam. F1, F2, F2 is here, F3, F4, no F4, G1, G2, G3. Okay, these forces are acting on the beam. However, inside the beam, let's take this section. We cut the beam here, the section here. Let's say a DS element inside. In this section, this small element will also have stress inside. So we need to determine this stress of our beam, the internal stress, not only the external one. Okay, it's like when you see boxing. Okay, when somebody is boxing you, you are receiving punches, but inside your body will feel the pain, okay, the stress. So inside the beam also, inside we have stress inside also. Stress is not only outside. So this is internal stress. Okay. So if we take this AB, this beam AB, the forces F1, F2, F3, G1, G2, G3, these forces are the applied forces, external applied forces. However, R prime, this R and R here, these are the reaction forces, the support reaction. Let's say, for example, you have here a column, here also a column. So this will support your beam. That's why we have reaction here, R. Okay. So if we take now the DS element, this small element in this section, you see this section, okay? The section S, the stress, when you see stress here, it means constant here, it means stress, okay? Stress, I will correct it. Okay, anyway, where again? Okay, so stress, this section S, this section we have here, this section. In this section, stress sigma and tau, T if we want. Sigma, you remember this one is normal stress. This T is shear stress. We have both in this section. In the way that this section, do you know this integral? Counter integral. Okay. ds. It means just the small element inside. If we, by additioning, by integrating all the small element, we can have this section. Okay. And also by integrating all the small means the normal stresses for each small element ds, we integrate all of them, we will have the total normal stress. By also integrating all the element means for shear stress, we will have the total shear stress, shearing stress. Okay, so the forces Fi being known, if we know all the forces acting on the beam, we can determine, we can calculate this reaction. This one and this one are. Okay. And in the following chapter, we will see many cases where you have to calculate the reactions if you know the forces, the external forces. Okay. We will do a lot of exercises on this. So for any section here, we can calculate the reduction element. Reduction element means S and M. So the stress and the moment. Okay. And the torso means the combination of the forces and the reaction. Fi and reaction. So for each element, we can get for each section of our beam or column or everything, we can check, we can have this element. Okay. Let's say now, consider that we have this same section here, is the same one. Okay. So if we take this, we consider S like the general resultant of the component N, Ty, and Tz. Okay, according to the axis is X, Y, and Z. And the M is the resulting moment, means we add the combination of the resultant of all the moment. resulting moment of the component mx, my, mz, okay, following these axes, these three axes. Okay, we can, N is the normal effort, the normal force, if you want. Please check here what section we are talking about, because the definition I'm going to give now, all the definition depend on the section we are working on. Here we are working on this section, this area, this area, this area, okay? So the normal effort, the normal stress or normal force are the force here perpendicular to this section. It means the force in this x-axis. That is very important. Any other effort will be sharing force, will be sharing effort. That will be the effort following the y-axis, or the z-axis. You can see here x, y, and z are tangent to our section here. However, this x is normal to our section considered here. It doesn't mean that anytime, every time, the x is the one that is normal to our section. Okay, just check which axis is normal to the section, or which force is normal to the section. That will be the normal section. And the other forces will be considered as shear forces. Okay, very simple. And my, mz, y is here, means moment around the z-axis, and the moment around the y-axis, moment around the z-axis. These two moments are the bending moment. Okay, if you do this, the beam will bend, or the beam will bend, supposing your beam is like this. However, if you take mx, moment around the x-axis, this moment will be torque. Okay, this moment will be torque, supposing this is our section. So you better understand this definition, because you are going to use it from now on until forever. You will use this definition. So you better understand the meaning of this definition. So it's easy. Just determine the axis that is perpendicular to the section you are studying. Which section you are studying, what is the axis that is perpendicular to that section. And all the forces that are perpendicular to that axis are also perpendicular, that are parallel to that axis, are perpendicular to your section. The forces perpendicular to your section are normal forces. And the moment around, the turning around the axis, the normal axis to your section, are the torque. All the other moments are bending moment. Okay? I hope it is clear. So we are going to stop here, and next time we will continue with maybe 2 or 3 exercises to end this chapter. Thank you very much for your time, and see you.